Good morning. Welcome to lecture number 19 in our series on silicon and wide bandgap power devices. I'm Professor Anant Agrawal at the Ohio State University. I'd like to acknowledge my colleague Dr. Arash Salami here with me at OSU, and of course the support of Office of Naval Research. So last time we studied the last few lectures, we studied the Schottky diode, reverse and forward operation, how to make it into a power device. Then Dr. Salami talked about the detailed processing and layouts of these Schottky power diodes. So today we will start a new chapter, and that is about the power MOSFETs. And before we get into power MOSFETs, I would like to say a few things about the MOSFET operation, because many of you may not have studied the basic MOSFET operation. So we'll not go into detail because one could spend the lifetime describing MOSFET operation, but we'll try to do it in a short, concise way today. And you can look into some references that will give you a lot more details if you're interested. So here is what we are talking about. On the left hand side is a MOS capacitor. It is called MOS because of metal-oxide-semiconductor. So essentially what we are showing here is a p-type semiconductor, could be silicon carbide. We are showing a thin layer of SiO2. This is normally thermally grown on the silicon or silicon carbide semiconductor. And then in old days we used to have a metal gate such as platinum or some other metal. So that's why the name stuck. It's called Metal-Oxide-Semiconductor. These days this metal has been replaced with polysilicon gates, which are doped N-type with phosphorus. So this is a basic MOS capacitor because the capacitance is formed between the metal gate and the semiconductor, and we'll describe the details of this operation. Then on the right hand side is called the MOS transistor, where we basically take the MOS capacitor and put two N plus regions into this, either by ion implantation or diffusion, and this becomes a transistor. This electrode is called the drain electrode. This electrode is called the gate electrode, and this electrode is called the source electrode, and here is the body. So we'll describe the operation of the MOS transistor, and then we'll show you how to make it a power MOS transistor. So in short, we will call it MOSFET, metal oxide semiconductor field effect transistor. And a lot of these details are available in this reference, which is available on the internet. So please look through this reference. All right, so let's concentrate on the MOS capacitor. So as we said, it's called MOS capacitor because of metal oxide semiconductor. This is also called the gate oxide or gate dielectric, which generally, as this picture shows, this is a high resolution TEM. You can see this is a semiconductor, this is the oxide, which is amorphous, and then this is the polysilicon, or this could also be metal. And here is a detailed picture of this. You can see this oxide layer is 16 angstroms of thick, and here is a polysilicon gate which is doped N-type or P-type, but mostly N-type with phosphorus. So, this oxide thickness can range from 5 angstroms to 1000 angstroms depending on the application. In the CMOS technology, where you have high speed digital and analog circuits, this oxide thickness is very, very thin, something of the order of 5 to 10 angstroms these days. But in power devices such as in silicon, this oxide thickness is of the order of 1000 angstroms. In angstrom, 16 angstrom, another unit for this is nanometer, so that would be 1.6 nanometers. All right. So, let us assume that this capacitor is at 0 bias, and you can see nothing is happening. Then as we apply the negative bias, you can see that in order to drop this voltage across this MOS capacitor, we will have negative charge in the metal gate and positive charge in the semiconductor. So, the positive charge in the semiconductor will consist of holes, and this layer is called the accumulation layer, meaning we have accumulated holes in a p-type semiconductor. So, then and the capacitance defined by this thickness, 2 parallel plates, is called the oxide capacitance, and that oxide capacitance will then drop this voltage, a negative gate voltage. So, this condition is called the accumulation. And then we have the left hand side again, which is called the depletion. In this case, we have applied gate voltage which is positive, but not too positive. So, in this case, in order to drop this gate voltage across this oxide, we need positive charge in the metal and negative charge in the semiconductor. So, the semiconductor which is p-type will deplete, and in this depletion region there will be no electrons or holes that are free carriers, and that is why we are left with negative acceptor charges in the depletion layer. So, these negative charges in conjunction with positive charges here help to drop the gate voltage across this sandwich. So, the part of the voltage will go across the oxide, and the part of the voltage will go across this depletion region. Basically, we have 2 capacitors in series here, the capacitance of the oxide and the capacitance of the depletion region. Then if we keep increasing the gate voltage above a certain value, which is called the threshold voltage, then we achieve a condition which is called inversion. So, what happens that this depletion region keeps expanding and then stops, and then we get additional negative charge here in the form of free electrons. So, remember these negative, this negative charge is due to the ionized acceptor impurities which are left behind because the holes have left, and then this negative charge is because of the free electrons that are in the conduction band. So, together these 2 sets of negative charges with positive charge in the metal gate will help drop the gate voltage across the oxide and across the semiconductor. And this layer of electrons is called the inversion layer. And it's called inversion layer because we have now changed the polarity at the surface from p type to n type. All right, so with gate voltage of less than 0 volts, we have accumulation condition. With gate voltage greater than 0, we have depletion condition, and if the gate voltage is sufficiently high, higher than the threshold voltage, then we call it an inversion condition. So, let us study this in detail with the help of band diagrams. So, we always know that electron concentration is given by this expression, and it's exponentially dependent on the Fermi level minus EI over KT, and the hole concentration is always given by this condition, which is exponentially dependent on EI minus EF over KT. If you multiply the two, you get n times P equals to Ni square. So, that is an equilibrium concentration of electrons and holes, the product being equal to Ni square. The individual concentrations can be obtained from these equations. All right. So, on the left hand side, we have a capacitor at gate voltage 0. Everything is in equilibrium. There are no charges anywhere because we are considering the ideal condition. So, the bands in the semiconductor are flat. So, you can see that the Fermi level is in the lower half band gap because it is p type semiconductor, and we can see that EI minus EF is greater than 0. That means EI minus EF is greater than 0 means we have lot of holes in the semiconductor since it is p type, and very few electrons, right, because P is equal to the doping of the semiconductor, and N equals to Ni squared divided by P, and P is equal to Na. So, we have very few electrons, lot of holes, the Fermi level is in the lower half band gap, and this situation is called the flat band condition because all the bands are flat in the semiconductor, and there is 0 voltage. So, there is no charge, there is no voltage anywhere. Then we apply depletion, which means we apply positive gate voltage, and as I described to you, we have negatively charged acceptor atoms in the depletion region. This is called the depletion region here. We have positive charge in the metal, negative charge in the semiconductor, and gate voltage is dropped across the oxide and across the semiconductor. Now, here in terms of energy band diagram, we are showing two conditions here. So, the first condition is the bands bend down. So, when the bands bend down, you can see EI minus EF is going to reduce as we move from bulk towards the surface, and therefore, the hole concentration reduces because it is a depletion region, and electron concentration increases at the surface, right, because EI minus EF is reducing near the surface. The gate voltage is dropped across the voltage across this oxide and across this depletion region. Then here we have increased the voltage a little more, and in this case EI minus EF is equal to 0 at the surface. So, if EI minus EF is equal to 0, then electron concentration is equal to the hole concentration. Electron concentration is equal to the hole concentration, and the Fermi level has the bands have been bent exactly by this potential phi f, which is the difference between EI and EF in the bulk. So, electron concentration is equal to the hole concentration at this gate voltage, and after that, if we apply the gate voltage even more, you get the inversion condition. So, as we described to you, now we have to bend the bands more because gate voltage is increased, and in this case now EI goes below the Fermi level. So, at the surface EF minus EI becomes positive and EI minus EF becomes negative. So, looking at these equations, you can see now that the electrons concentration increases, hole concentration reduces, and the condition at which the bands bend exactly equal to 2 phi f, that means the intrinsic level is below the Fermi level at the surface by phi f, then the total band bending is 2 phi f, and at that point the semiconductor has inverted, meaning we have now lot of electrons, very few holes. In fact, the number of electrons here in inversion are equal to number of holes in the semiconductor at 0 gate voltage. So, now we have completely inverted the situation. The number of holes have gone down, number of electrons have gone up, and at this point, if we apply any more gate voltage, the bands bend very slightly and we get lot of electrons here. So, at this point, depletion region stops expanding and we call it the maximum depletion width, WD max, and this voltage at which this happens, that means this voltage at which the total band bending is 2 phi f, is called the threshold voltage in semiconductor. And the maximum depletion width is WD max, and you can see from Gauss's law that total potential in the semiconductor would be equal to Q times Na times WD max square divided by 2 epsilon s. All right. So, by essentially applying very high gate voltage higher than the threshold voltage, we can achieve an inversion layer, which is a free electron layer, a very thin layer of free electrons at the surface of the semiconductor, and this layer is called the inversion layer. If we apply voltage which is less than the threshold voltage, then we have a depletion condition, we do not have the inversion layer. But if we apply enough voltage greater than the threshold voltage, then we have the inversion layer. So, now going back to our previous diagram, we can now talk about the MOS transistor. In MOS transistor, we have two additional terminals, source and drain, and assuming we ground the source, we ground the body, we apply positive voltage on the drain and we apply positive voltage in the gate, we will form electron inversion layer here, provided gate voltage is higher than the threshold voltage. So, if we apply gate voltage higher than the threshold voltage, we will form an inversion layer of electrons here, and you can see a current can start flowing like this. So, for gate voltages less than the threshold voltage, there is no inversion layer, there is no conduction from source to drain. So, the current is 0. So, the current is 0 all the way up to gate voltage equals to slightly below the threshold voltage, and at threshold voltage we have this inversion layer present. So, the current can flow from source to drain, drain being positive voltage, the electrons will flow from source to drain, and that means the current, conventional current will flow from drain to source. Now, the MOSFET characteristics for gate voltages greater than the threshold voltage look like this. They are initially linear and then they saturate, and they saturate because after a while all the electrons that are present here contribute to the current. So, without going into too much physics of this, we can represent the straight line, or this is called the linear operation and this is called the saturation operation. For linear operation, we can show that the current is proportional to W over L(ox), oxide capacitance, which is given by epsilon ox over d ox. Epsilon ox is the dielectric constant of SiO2 times the permittivity of free space times the inversion layer mobility times Vgs minus Vt. That means how much gate voltage is in excess of the threshold voltage Vt times Vd, and then there is a small term here represented by Vd square over 2. So, you can see that in the linear region, the current is proportional to the width of the MOSFET, inversely proportional to the length of the MOSFET, and proportional to the oxide capacitance, proportional to the inversion layer mobility, and proportional to the drain voltage. So, you can see that if we make W larger or L smaller, the current is going to increase. If we make the oxide thickness smaller, which means we increase the oxide capacitance, the current is going to increase. And if we increase the inversion layer mobility, then the current is going to increase. Now, one word about the inversion layer mobility. In silicon, this value is roughly half of the bulk electron mobility in semiconductors, which we had studied in some early lectures. So, the electron mobility in p-type or n-type semiconductor, we know is bulk mobility is determined by the Coulomb scattering and the phonon scattering, and we had studied all that, and it is a function of doping. But the inversion layer mobility tends to be about 50% of the bulk mobility. So, if the bulk mobility is 1000 centimeter square per volt second, the electron mobility at the inversion layer would be about 500. All right, then these characteristics saturate here, and the saturation current is given by this equation. In our power transistors, we will mostly operate along this linear region. So, it is important to understand that the characteristics do saturate when the drain voltage is equal to VGS minus VT, and at that point there is no channel next to the drain. The inversion layer disappears next to the drain, and all the current that's flowing into the inversion layer just gets collected by the positive voltage in the drain, and that's why the current saturates. So now we can show that the resistance of the MOSFET in the linear region is simply VD over ID. Is simply rearranging this equation, we get an equation for the resistance of the MOSFET in the linear region. So here are some experimental characteristics taken from this reference below. In this, we have taken a silicon MOSFET which has a channel length of 10 micron, width W is 10 micron, oxide thickness is 4 nanometer, that means 40 angstrom, threshold voltage is about 0.3 volt. You can see that for gate voltage greater than threshold voltage of 0.3 volts, in this case 0.5 volt, we can see a little bit of drain current. At gate voltage of 1 volt, we can see that current starts flowing, and as we increase the gate voltage, more and more current starts flowing. And you can see that the knee voltage is roughly VGS minus VT. And we can continue to apply this gate voltage, and we will continue to get more and more current out of this device. Now, VGS minus VT is given by this red line, and you can see the knee voltage roughly aligns with this red line here. And to the right of the red line, we have saturation characteristics. To the left of the red line, we have linear characteristics. Then here we compare two silicon MOSFETs. On the left is short channel MOSFET, which is L equals to 0.15 micron. This is called short channel. It is sub-micron channel length. Threshold voltage is about 0.4 volt. On the same mask, we have on the same design, we have a channel length of 2 micron, which has a slightly higher threshold voltage of 0.7 volts. One major difference you can see is that, first of all, the current is much higher in the short channel device, because remember, the current is given by W over L. The W in both of these cases has been taken as 1 micron, so the current is represented as milliamps per micron. So the W is 1 micron in both cases. So now you can see that because of the short channel length, we have a lot more current in the left hand device. And then in the saturation characteristics, you can see we have an output impedance which is very high in the long channel device, meaning the characteristics are totally flat. And in the left hand side, you can see the characteristics are not totally flat. The current keeps increasing. That means we have a finite output impedance, and this is the effect of the short channel, and this is called the short channel effect. So other than that, over the last 30-40 years, there has been a trend to increase this channel length from 10 micron to today about very small, something like 50 to 100 angstroms. and then the gate voltages have been scaled from 10, 15 volts long time, 30 years ago, to something like less than 1 volt today. So there has been a tremendous progress in making these MOSFETs over the last 40 years or even 50 years, where the main trend has been the reduction of channel length and reduction of the gate oxide. And therefore, we make the transistor smaller and smaller and we get more current out of it. Now, we also have a p-channel transistor, which is very similar to n-channel transistor. The transistor we have been describing is called the NMOS or n-channel transistor because the inversion layer is made of electrons. The PMOS or the p-channel transistor is exactly the opposite of the n-channel transistor, and the inversion layer consists of holes, and you can see the hole mobility is roughly 1/3 of the electron mobility. Therefore, for the same geometry, we get roughly 1/3 of the current in the PMOS transistors. Together, NMOS and PMOS in a technology, when they exist together, the technology is called the CMOS technology, and today a lot of digital and analog circuits consist of CMOS transistors, that is both NMOS and PMOS transistors. In power devices, we have not used the PMOS transistors because the hole mobility is less than the electron mobility, and therefore, the power PMOS transistors are not widely used. Thank you very much.